Hey, algebra students. In this lesson, we are going to be talking about factoring special products. Previously, we had a lesson on special products, and you may remember that special products are special sets of binomials that we can easily multiply together because they follow a pattern of how they multiply together. For example, x plus 6 times x minus 6. It's always going to be a difference of two squares. The first number squared minus the second number squared, x squared minus 36. You see, we have one of those down here. X plus 7 times x minus 7 multiplies together to become the first term squared, x squared, minus the second term squared, 49, difference of two squares. The difference in this lesson is that we're going to be working that pattern in reverse. Notice I didn't start with x plus 7, x minus 7 on the left. On the left, I have x squared minus 49. What you need to do now is be a detective looking for these patterns in trinomials. So do you see the difference of two squares? A square number, a perfect square number, minus another perfect square number. Or do you see a set of numbers like we have up here? Remember, if we have a binomial squared, x plus 6 squared, when we square that, it's going to turn into a trinomial with a pattern. The first number squared plus 2 times the first number times the last number. 2 times x times 6 is 12x, plus the last number squared, 36. If the middle number is negative, if it's a x minus 6 squared, then the middle number is going to be negative, right? So what you're going to have to do is look for these patterns and be able to identify them. Also, notice that sometimes the question is it a perfect square trinomial? Is it the difference of two squares? If it's not, you have to be able to recognize that it doesn't fit one of the special patterns and it can't just be factored by pattern. Okay, so the key takeaway from my intro here is that what we're going to be doing is following special patterns related to special products, okay? Now, we're going to work some practice problems here, and we're going to just emphasize the special patterns that we're following as we work these problems. We're going to start with letter A, and down here what we're doing is we're determining, first of all, is this a perfect square trinomial? Does it fit the special pattern? If it does, we can factor the trinomial. So let's go with letter A. I'm just going to write out the problem here and notice that I made one little adjustment. Instead of just calling this x squared, I put the coefficient 1 in front because you can always put a coefficient 1 in front of a variable that doesn't have a coefficient. There's an implied 1 there. Now, the question we need to ask ourselves is the first number a perfect square? 1x squared? Yes. It's the square of just x, right? Is the last number a perfect square? Yes. If my answer to either of those questions was no, I could say that this is not a perfect square trinomial. First number has to be a perfect square. Last number has to be a perfect square. Now, this isn't difference of two squares. This is one where we have a term in the middle. I have to ask myself, is the term in the middle 2 times the square root of the first term times the square root of the last term? 2 times x is 2x, times 7 is the square root of 49, right? So 2 times x times 7 is 14x. Yes, this is a special pattern. So the answer here is going to be yes. And then I can factor the trinomial. Well, I'm always going to factor it by pattern. It's always, let's see, now I have a plus in the middle. So that means that it's going to be something plus something squared, okay? Because there's a plus sign here. It's a squared binomial. And then the thing that's going to be squared is the square root of the first term and the square root of the last term, x plus 7. So it's going to be x plus 7 squared, or x plus 7 times x plus 7. All right, this is exactly what we did with special products, except it's in reverse. If we were doing lesson 60 all over again, I think it was lesson 60 where we did this the first time, what we would have to do is figure out how x plus 7 squared turns into this trinomial. Now you're going to be expected to see a trinomial and be able to determine if it's a special product. Let's take a look at the next one. Is the next one a special product? Notice down here it's 6n to the fourth minus 12n squared plus 6. One of the things I noticed as I wrote this out here, I could factor a 6 out of everything here. Factor a 6 out of the first term, the second term, and the third term. Now, I have to ask myself, after I factored out the 6, is this new term in parentheses a perfect square? The first one, is this a perfect square? N to the fourth is n squared squared. So yes, the first term is a perfect square. Is the last term a perfect square? 1 is always a perfect square. It's 1 times 1. So I do have, now I'm not saying for sure that this works, but right now it's looking good. I have to ask myself, is the middle term 2 times the square root of the first term times the square root of the last term? 2 times the square root of n to the fourth is n squared, times 1 is 2n squared. It fits. One other thing I notice is there's a minus sign here, okay? So this is a special product problem. It fits this second pattern right here. A number squared minus 2 times the square root of the first number times the square root of the last number plus a last number squared. So what I need to factor this out, it's going to be the square root of the first term squared. I'm sorry, the square root of the first term minus the square root of the last term squared. What's the square root of n to the fourth? It's n squared. Square root of 1 is 1. This is going to be, I have to make sure I bring my 6 along. N squared minus 1 squared. Okay, so everything in parentheses here turns into n squared minus 1 squared, and then I need to multiply that whole thing by 6. Letter C. Does this fit the special product patterns? 3g squared plus 9g plus 9. Well, first thing I'm going to do is factor out a 3. Maybe if I factor out a 3, this will become something that fits one of the special product molds. Let's see if it does. Oops. All right, so here I have 3 times g squared plus 3g plus 3. G squared plus 3g plus 3. Okay, so the first number is a square, but the last number is not squared. Because the last number is not squared, the answer to this one is no. This one is not a perfect square trinomial or a difference of two squares. It doesn't fit any of the patterns because my last number, no matter what, my last number has to be a perfect square. And then even if my number was a perfect square, the middle number has to be 1/2 times the square root of the first number times the square root of the last number. And that middle number is not going to work either. Nothing else I can do here. If it's not a perfect square, I can't factor it using one of the special patterns. So we're going to move on to letter D. Letter D, okay, I just wrote the main part of the problem up here. In letter D, it says a radio tower signal covers a circular area with a radius r in miles. Okay, so the radius is r. Hey, what do you suppose the area of that radio tower's coverage is if the radius is r? The area would be pi r squared. Pi r squared is the area of a circle. So this is going to cover a circular area of pi r squared. The strength of the signal is increased, and now it covers an area with a remarkably difficult to figure out value for area. I mean, what is pi r squared plus 12 pi r plus 36 pi? That seems pretty complicated. All right, now, here's the thing. We can uncomplicate this a little bit. It asks us how much did the radius of the coverage area increase, and you're probably scratching your head right now saying, what in the world do I do to figure this one out? Well, let's do what we've been doing. Let's see if this is a perfect square trinomial. Now, the first thing I'm going to note when I look at this right here is that there's a pi in every term. I can factor that pi out front. Notice that that's what I've done here. When I wrote down the problem for letter D, I put pi in the front, and then it's r squared plus 12r plus 36. But wait a second. I'm looking at this, and I'm seeing I'm starting with a square term, r squared. I'm finishing with a square term, 36. And the middle term is 2 times the square root of the first term, r, times the square root of the last term, 6. 2 times r times 6 is 12r. Because that's true, this fits one of the special products. This fits the special product right here. A squared plus 2ab plus b squared. So what does that mean? That means that I can actually take this and apply my special product to it. It becomes pi times r plus 6 squared. Pi times r plus 6 squared. Now, I didn't put a pi in front, but I am just going to emphasize this. R plus 6 squared means something important. So wait a second. Before, our coverage radius was pi r squared. Now it's pi r plus 6 squared. How much did the radius increase? Just the radius. Well, before it was r, now it's r plus 6. So we would say that the radius increased by 6 miles, okay? That one's a really tricky one. Those ones don't come up too often in the homework, but just kind of be ready in case they do. You're just looking for special patterns. All right, let's jump to letter E. Letter E. Determine whether the binomials is difference of two squares. Now you can notice I just jumped to writing yes for this one because it's super obvious. Is the first number a perfect square? 5x squared is 25x squared. Yes. Is the second number a perfect square? 4 is a perfect square. It's really easy to identify for difference of two squares problems because there is no middle term. We're just looking at the first term, looking for the last term. If it is, we need to factor it according to a special product. It's going to be the square root of the first term plus the square root of the second term times, so that quantity times the square root of the first term minus the square root of the second term. So it's going to look like this. 5x plus 2, 5x minus 2. The square root of 25x squared is 5x. Square root of 4 is 2. 5x plus 2, 5x minus 2. Is f a perfect square at the beginning and a perfect square at the end to become a difference of two squares? The other thing I didn't emphasize in the first, it has to have a minus sign in between. Or you have to be able to rearrange it so it has the variable term minus another square term, okay? All right, let's see if this one fits the pattern. 9b squared minus 100a squared. Yes. I noticed that 3b can be squared to make 9b squared. 10a can be squared to make 100a squared. So this is going to be 3b plus 10a, 3b minus 10a. I'm just following the pattern. That's all I'm doing. G is not a perfect square trinomial. I'm sorry, a difference of two squares, because 14 is not a perfect square. What about this one? It has a plus in between. But I can rearrange it so it becomes x to the 10th minus 81. If I rearrange it into that order, it is the difference of two squares, which is x to the 5th plus 9, x to the 5th minus 9. And then lastly, letter I. Square border is designed around a square pool. Let's just zoom in here. Use the difference of two squares to write and factor an expression that represents the area of the border. So I need the area of this. What I'm going to do is I'm going to take the area of the outside square. That's going to be 34 squared minus the area of the inside square. 34 squared minus s squared. Well, let's just see how this one plays out. So 34 squared minus s squared is going to give me the area of this border out here. I take the area of the big square minus the area of the small square. Am I able to factor this? I don't even need to write out what 34 squared is or punch it into a calculator. All I need to do is determine this is difference of two squares. It's going to be 34 plus s, 34 minus s, according to the pattern. And then I just throw in a label at the end, feet squared, and that is my answer. That is how you work problems with special products.